Over the past 20 years, urban areas have experienced a dramatic growth in population numbers, and it is expected that this growth will not come to a halt anytime soon. According to the World Health Organization, by 2030, 80% of European population will live in cities. This is the result of population growth and a transformed economy due to radical technological and political change. At least 27 of these cities are expected to become so-called megacities, having upwards of 10 million inhabitants. Needless to say is that these developments bring with them a list of new urban problems related to personal and freight transportation, congestion and environmental impacts. In addition to this, there are many other ways in which an increase in the population size can make life in the cities less comfortable. Fortunately, technology is also able to offer an interesting solution to these problems. Just like the internet has allowed many benefits and efficiency increases in the intangible information space, the Internet of Things has the ability to provide great benefits in the physical space. Just as with the regular internet, the Internet of Things becomes more powerful as more and more devices are added. A promising application of IoT technology in physical space comes from the concept of smart cities, which are defined as cities in which the ICT infrastructure is merged with traditional infrastructures, coordinated and integrated using new digital technologies. This makes clear that technologies that are developed separately but clearly could supplement each other to provide new opportunities need to be coupled. There are already real-world examples of the applications of IoT in the development of smart cities. For example, in a joint project between the municipality of Amsterdam and tech giant Google, a variety of mobile and static sensors is used to assess the availability of parking space throughout the city. Through a pictogram in the Google Maps smartphone application, users navigating through the city are informed of the availability of nearby parking space. Of course, such a project is relatively limited when compared to the possibilities of IoT, but the adoption of these ideas in practice is great news for the development of smart cities. An important factor in IoT systems is the architecture, or the way the system is organized. This presentation will examine a proposed system that could enhance the architecture of many IoT systems. This system is targeted at resolving the complexity involved with a huge amount of different IoT objects in smart city systems. As with many IoT systems, the vision behind smart cities is that a wealth of data, collected by an enormous amount of different kinds of sensors spread throughout the city, will enable us humans to organize and act in more efficient ways. This is one way that we could deal with the previously mentioned megacities of the future. There is, however, one fundamental problem, which has been bothering big data and IoT professionals for years. We've got this huge pile of data and a huge collection of sensors, but how do we extract meaningful information from it? Information that we can actually use in practical applications that make our lives better. Currently, there are two important factors that significantly limit the applicability of IoT systems and data for large-scale smart city problems. These are the heterogeneity of objects and the object application proximity. The heterogeneity of object refers to the fact that there is an enormous variation in the types of devices that are employed within IoT systems. These devices do not only vary in terms of their function and physical appearance, but also in terms of data format, communication protocol and the way they identify themselves to the network. This also relates to the concept of proximity, which refers to how close two entities are to each other. In the case of IoT, it acts as a metric of relevance, concerning how relevant an IoT object or device is to a specific IoT application. These concepts are strongly related, as the large heterogeneity of objects makes it quite difficult to assess their proximity to a specific application. Therefore, even though many IoT sensors are available, it might be difficult to figure out which one can be used to reach a specific goal. 10 researchers, which have collectively proposed a solution, therefore state, we have identified the need to support end users and application providers with techniques that can automatically select by relevance all potential objects discovered to be available for use and able to meet given application requirements. If successful, this system could greatly increase the amount of practical applications possible for smart cities. The solution that these researchers proposed is called the Cognitive Management Framework for the Internet of Things. This framework would overcome the limiting factors and could significantly boost the development of smart cities. Based on the mechanisms proposed in this framework, IoT systems would be able to autonomously and intelligently organize IoT devices, the so-called real-world objects, into virtual or composite virtual objects, based on a specific application requirement. The great benefit of this is that the application or service layer is even more abstracted away from the hardware layer of the IoT devices. Instead, it hides all of the complexities of working with many different IoT devices on different networks and different standards, and presents all objects in a standardized way, the virtual objects. Semantically similar virtual objects can in turn be grouped within composite virtual objects, which can provide new services based on existing virtual objects. These virtual objects are key, as these are the objects that the Cognitive Management Framework interacts with. This makes sure that, although the real-world objects or IoT devices on which they are based are vastly different from each other, the virtual objects the system can see are all similar to each other. A virtual object or a composite virtual object is thus characterized by the service it is meant to deliver. Important to note is that a single virtual object can therefore obtain its function from multiple real-world objects, such as IoT devices. Composite virtual objects are therefore also able to self-reconfigure if the context of their service changes, autonomously maintaining their performance over time. Virtual objects are enriched with semantic data that will allow cognitive mechanisms to assess the proximity of virtual objects to each other or of composite virtual objects to a specific application. Although originally reserved for humans, the term cognition in this case refers to working with and understanding information. The Cognitive Management Framework, as the name suggests, makes use of cognition throughout the system. For example, at the lowest level, in the self-management and self-configuration of the virtual objects. Here, cognition is used to manage links to the relevant real-world objects, selecting those that best serve its function. At a higher level, cognition is used to select objects that meet application requirements. For example, pattern recognition is used to identify existing objects that can be reused, and optimization techniques and learning are used to facilitate the construction of new objects. At the highest level, semantic reasoning is used to automatically translate application requirements to a request for a service that can be met by composite virtual objects. The researchers have identified the need for a system which will automatically select available IoT objects that meet application requirements. This is due to the fact that a huge number of available devices makes it very difficult to assess which one could benefit a specific application. Therefore, many great smart city applications are unnecessarily difficult to implement. The Cognitive Management Framework for the Internet of Things is proposed as a solution to this problem. As discussed, the system would construct so-called virtual objects based on real-world IoT objects and would tag them with semantic data. Once the application requirements have been automatically translated to the system language, it can then identify the virtual objects that would benefit the application. The major benefit of this system is obviously the fact that it's able to abstract away from the many layers of complexity caused by the large differences between IoT devices. Instead, it preserves the device function but presents it to the system in a uniform way through the virtual objects. Since these virtual objects can be easily examined, the system is able to automatically select them. This has dramatically decreased the impact of the large heterogeneity of objects. A second benefit is that each of the virtual objects or composite virtual objects are tagged with semantic data. This makes it easy to examine each object's properties and examine the proximity between a virtual object and the application requirements. Therefore, objects that meet application requirements can be easily selected. With these two benefits, the cognitive framework for the Internet of Things is able to meet the demands of the problem statement. Furthermore, these two benefits correspond to the problems identified, heterogeneity and proximity. Therefore, this framework is seen as a viable solution. In our opinion, there's little to dislike about this system. Although we have mainly focused on the innovative parts of this system, its resilience and security are also convincingly described in the paper. The only shame is that some parts of the system still need to be defined in detail, and a convincing proof of concept still needs to be constructed. However, since the paper essentially proposes a brand new framework, these points are not fair critiques. Instead, it is normal that more work is necessary before such a novel framework can be expected to work in practice. It is our hope that development will continue. For now, it seems like the researchers have done a great job in advocating the promises of the cognitive framework for the Internet of Things.